does it increase the amount of electrons emitted then?
Yeah, yeah, you increase the amplitude, then higher, it will, once you meet that minimum, the brightness will increase your number of electron. Okay? Below this threshold, we call that threshold frequency. No electron will be emitted regardless how long or how bright it is. You could keep shining the low intensive light for a long time, it will not happen. High frequency though will eject the electron even if the intensity is low. It's just fewer number of electrons get ejected. Is that clear? Yeah? Any questions? All right, yes.
Do we need to know the other types of photoelectric effects, such as the photon exciting the electron to then be released by the atom?
Yeah, that's the next thing.
Oh, sure.
Okay, so we have to somehow have to explain the discrepancy. Explains what we think it should be, right? Actually, it takes a while until 1905, this way Einstein took him to explain that. He said light must come in particles, in packets. Packet meaning particle, right? Which are called photons. He's thinking that for energy, light come in discrete packets. He called it photon. Okay. The amount of energy in a light packet, one photon, is related to its frequency. E photon, the energy of the photon, equal to h nu. What's h? H is a constant. It's called the Planck's constant. Nu is what? It's frequency, right? So the energy of a photon depends on frequency, but does not depend on amplitude. Just each individual package. So the energy of light comes in as packets, okay? But not continuous. You can just add them up like that, okay? So that you can add up two low energy photons to do the job of kicking the electron up, okay? So as the energy of light, which is proportional to the frequency, increase past the threshold, the excess energy of the photon is transferred to the electron in the form of kinetic energy. What if I put in more than the minimum frequency? Then not only I could eject that out, I could also give out, also give the electron with kinetic energy. If my frequency is high enough, I could overcome the binding energy or the metal for that electron. And also the excess light energy going to transfer to the electron, find out faster. Okay? Does it make sense? So, and that excess energy turned into kinetic energy of the electron. This binding that photon's energy going to equal to first overcoming the binding energy because the electron get held by the matter, right? It's called binding energy. You hold on to it. Only the light coming in with enough energy, you could overcome that. If any excess, going to transfer to the electron. And that's why the light energy, E photon, going to equal to this two. First, you got to have enough to overcome the binding energy. Secondly, any excess going to transfer to the electron, give it kinetic energy. Does that make sense? All right, so let me go back a little bit. Let's see. So going back to this ejection of the electron, you can think of it like this. Say if I want to get Thomas out of the seat, I can keep slightly pushing him, I spend enough energy, but he's not going to get out. I need someone have enough big push, that one push has to do the job. You cannot just kind of slightly push him a little bit. Even the total energy add together is the same, but each one is not enough to get that big push. Okay, in order to push it out, you gotta have someone strong, have to give a big push. Okay, if I just tap it a little bit at a time, if I tap 1,000 times, it's not gonna have enough energy. So the same thing with the light coming in, it comes in with certain energy. You cannot just add them together to become one big energy push. Does that make sense? So that was the reason. Got to have one individual one. One packet had to have enough to overcome the binding energy in order for that to happen, for the electron to get ejected. Okay? All right, knowing that, we can do some calculation. So what is the energy of 57 photons? So light coming in sometime appear to be coming as wave, but other times as far as energy goes, it comes in packets of energy. Okay, those are packets of energy. In that sense, we say light behave as particles. Its energy is not continuous, it's in packets. Okay, so that packet had to have enough for it to reject the electron. Okay. So knowing that, what is the energy of 57 photons or electromagnetic radiation that has the wavelength on this value? What type of radiation is this? So I'm saying that I have 57 of these packets of light energy. So 57, we call 57 photons. You can think of a photon is a packet of energy. So what would the total energy be? What's the energy equal to? What? Yeah, you had to find each photon's energy, right? Because we were able to say, well, each of the photon is equal to what? H nu. What's H? Planck's constant is a fixed value. What's nu? Frequency. Do I have everything here? I do, right? Because the H has a value of 6.626 H, and the value is a fixed value. That is 6.626 times 10 to the negative 34. It has a unit of joule times second. Okay, and the frequency is what? We don't know, but we do know the wavelength. That they're related. How are they related? So we're going to relate by C over lambda, right? Frequency over. Remember how they relate the C equal to lambda times mu? I'm looking for frequency. C was C again? We're talking about the electromagnetic radiation. So therefore is 3.0 times 10 to the 8 meters per second. And then the lambda is 10 to the minus 1 nanometer. Nano means what? 10 to the what? Minus 9. Okay? So multiply that out, you can see unit cancel out. I always want you to pay attention to the cancellation of unit. So if the unit don't cancel out, meaning what? You probably set that wrong. Okay? So let's see, meter cancel out. And second cancel out. I'm end up with what kind of unit? Joules, which is the energy unit. Nothing but joules, right? So that's only an energy unit, and that's what I want. So, let's see, what is that? Equal to 1.98. 1.9878 times 10 to the minus 15 joule. Okay, it is joule for 57 photon?
No, for one photon.
So it's only for one photon, okay? So that is, just understand that's one photon, okay? That is understood, that is per photon. Now, do I need how many? 57 photons. 57 photons of this kind, of this wavelength, of this wavelength, then we go to 57 photons. And each photon has 1.9878 times 10 to the minus 15 joules per photon, which is understood, you know. So you add that photon. So photon cancel out, you get your total energy is 1.13 times 10 to the minus 15 joules. As far as which region, it turns out I'm referred to the electromagnetic spectrum. Okay, refer to electromagnetic radiation spectrum. It turned out it fall under, it turned out to be X-ray. Okay, you look back to the whole spectrum and see where it went. Is that good, everyone? Can I move on? All right, next problem. Okay, here we go. I'll give you a couple minutes to think about that one. So you have a nitrogen laser which put out a pouch which contains this much energy, millijoule, 10 millijoules of energy at a wavelength, this wavelength, lambda equal to that number. How many photons is this? How many photons? It's almost, you know, each photon's energy, and totally also know the total energy. So how do you do this one?
Find the energy per photon.
Yeah, I find out the energy per photon, E per photon. Whenever you're talking about energy of photon, what equation do you use?
H nu.
Yeah, E equal to H nu. So do I know the nu? Do I know nu? I have to find out. H is 6.626 times 10 to the minus 34 joules. Times second, that's what this unit is. And times nu. Nu is just what? C over lambda, right? Where those two multiply together equal to C. So therefore 6.626 times 10 to the minus 34 joules times second. And C is 3.00. This time I actually use a better, because everything is 4 sig fixed, I cannot use 3.00, right? Or all the given is 4 sig fixed. I want to use a better number. We say 2.998 times 10 to the 8 meters per second. So that will give me more than 4 sig fixed. But the other ones are 4 sig fixed.
We will use like 2 seconds for the energy.
Oh, I can see that. Okay. But in the, as far as this goes for now, well, this is in 4 sig fixed. I did calculate that later. Okay. Divided by lambda is 337 drop my name to make the actual unit, actual value, 10 to the minus 9 unit. Because I want to cancel out the unit. So this one turned out to be 5.893 times 10 to the minus 19 joule per watt. Per photon, understood that. Okay, so now, I know I have n photon, n number of that photon, right? N of energy of n photon, together equal to what? You know? 10 millijoules, right? So 10 millijoules, which amount to what in terms of joules? That would be milli meaning what? Milli meaning 10 to the negative 3. Okay, so therefore I have to say 1.0 times 10 to the negative 2 joule is equal to the n. I'm not sure what that is yet, so I'll just say n times each one. And each one is what? 5.89 and 4.893 times 10 to the minus 19 joules per kilogram. Can you find out the n value? Yeah, you should be able to find out n value. N is going to equal to 1.0 times 10 to the minus 2 joules. Divide that by 5.893 times 10 to the minus 19 joules per photon. So you end up with a photon unit. How many photons? It turned out to be 1.6969 times 10 to the 16 photon. Okay. Now I'm going to do my recipe. Before it wasn't. Okay? Anyone? Have any questions? No? All right, now, yes.
Photon has mass.
Say again?
Does it have mass? Does photon has mass?
Photon has no mass. Yeah. That's the thing. Like when we talk about particles, like atoms, protons, neutrons, they all have mass. But this one, photon, is more like you can think of as packets of energy. Energy has no mass, right? So you can think of that. Okay. So even the wave come in, have ups and downs in cycles, but the energy is actually in packets. So that's why sometimes it behaves like a wave, depends on what you're looking at. Sometimes it's a particle, in the sense it's energy coming in packets. Okay? All right, let's go to number
Professor
6. Yes.
Could you explain again why you used 2.998?
It's just so that I have a good, so because this C value is a constant. A lot of times, I just want to rough to 3 sig fig, then I will use 3.00. There's only 3 sig fig. But since the H is in what? Is it giving 4 sig fig? I don't want to compromise my sig fig. I will choose the C. The C, you could use the minimum, you should use 3 sig fig. 3.0, but you want to have more sig fig, then we'll use the other number.
So would it come out wrong if you use 3.0?
It'd be very slight. Okay. But this just, I'm just being careful.
So we could still use 3.0.
But then you'll end up with 3 sig fig. In this case, it's fine, because then you end up with 2 sig fig. Okay? All right, move right along, number 6. So you have binding energy for the electron to chromium metal is this much. So you have a piece of chromium metal. Chromium metal consists of what? Chromium atoms, right? So it consists of chromium atoms. I'm just using a circle to represent that. So chromium atom consists of this nucleus, right? And also have one or more electrons outside of it. So you have 3 electrons, more electrons, many, right? Electrons, how many? So you can look that up from the periodic table. So those are electrons outside. So if I have, so these electrons actually attract to the nucleus. Okay, so we call that the bonding energy. How much you attract to the nucleus, right? So it bond to the surface, you can think of it. So it's bonding to the surface. So in order to eject that, because it has some force, hold them onto the surface, okay? So now you can have light coming in, try to kick it out, okay, try to kick. So first you have to overcome the energy that's holding it onto the surface, right? And then any excess is transferred to the metal. So there's a minimum energy we need to overcome. That minimum energy refer to what? Refer to as what? Binding energy. Okay, what's the energy to hold it onto the surface? That's the binding energy. So binding energy will corresponding to the minimum energy you will need to kick it out. Minimum, that means you have shorter wavelength or longer wavelength. Shorter? Remember, wavelength and frequencies are inversely related. Higher the frequency, higher the energy. When we say minimum energy, going to be low frequency, meaning long wavelength. Okay, that's why they say the longest, meaning the minimum energy. Okay. Okay, when they say longest wavelength, that will correspond to lambda, the longest length. Lambda, that is, that lambda is going to be equal to minimum energy. Lambda, longest, meaning the smaller minimum energy. Is that clear, everyone? So you had to know those terms. Longest wavelength meaning what? Lowest in energy. Okay? You will eject. What's the lowest energy you will need? That's equal to what? The binding energy. So you minimally, you get to loosen that up. You got to dislodge that electron. Okay? Is that good? So that will mean longer we will eject from the chromium. That meaning minimum energy. Okay, what would the energy be? How would you calculate that out? Maybe you should write some notes first. Okay, electron bound to the surface with binding energy is something we call. How much energy required to get it, to dislodge that? In order to dislodge that, electron is somehow attached to your, the surface of your metal in order for it to kick it out. So your one photon is highlighted. In order to kick someone off the seat, you gotta have enough energy, just one big push. So what's the energy of that one big push? So that's exactly we go to define the energy, okay? So, and then how do you calculate the photon's energy? How do you calculate one photon's energy? E equal to h nu, right? By this equation, we gotta know this equation by heart, right? Otherwise we can't calculate anything. But I'm not given you ask for what? Wavelength, didn't ask for nu. You just rewrite that as what? Hc over lambda, right? So because I can relate the energy either with nu or with lambda, okay? So we calculate by that. So now we can do APOS. APOS has the minimum energy. Is what? How do you calculate that? So you just say what? Hc over lambda, meaning E photon. That photon, in terms of, I'm using the lambda equation, must equal to what? The binding energy. Okay, so can I find out the lambda then? Lambda equal to what? Hc over binding energy, right? So H is 6.626 times 10 to the negative 34 joules times second. C, let's see what it is. All those numbers are given in 2 or 3 sig, so I could use the 2.0 times 10 to the 8 meters per second. See, in the problem, right? Those numbers are giving you energy in 3 sig or in 2.5, 2 sig. I'm safe to use the 3.5. So we put that divided by binding energy. What's the binding energy? 7.21 times 10 to the minus 10. So I solve for that. I solve the lambda, turn out to be 3.76 times 10 to the minus 7 meters. So if I don't want to have such a huge negative exponent, I could just rewrite that as well. If I don't want to use this 10 to the minus 7 a lot of times, this is fine the way it is. If you want it to look better, you could just say 276 and that's what I gave you. Okay? Does it make sense, everyone? Now let's go to the B part now. There's the frequency required to give the electron with a kinetic energy of 2.5 times 10 to the negative 19 joule, okay? In my space, I'm gonna do it in here, part B. SU4 the frequency required to be. So not only I want to give it to dislodge the electron, but I also want to do what? Give some kinetic energy so that it could fly away from the surface. So the equation we use is equal to the photon energy, the coming, the instant light energy must equal to, first, you gotta possess enough to dislodge that, divide the energy for the electron. The remaining is gonna become what? Gonna be kinetic energy of the electron, and that's an equation. If you only want the minimum, just kind of loosen that up, you don't, can fly away, right? And then, if you wanted to fly away, so you gotta have kinetic energy. So that photon's energy, but the photon's energy usually we express that in terms of lambda or mu, right? Where they ask for what frequency. So that will equal to h nu, right? I don't need to use this serial one, but only if we use the wavelength, then you will need to use the h over length. So that is going to equal to binding energy plus kinetic energy of the electron. And so if I want to find out what the frequency should be, then it will equal to binding energy plus the kinetic energy divided by h value, the Planck's constant. So binding energy is, what's the value again? The 7.21, right? Times 10 to the minus 19 joules, plus the kinetic energy of the electron once it gets loosened up and fly away. So that'll be 2.5 times 10 to the minus 19 joules, divided by Planck's constant, 6.626 times 10 to the minus 34 joules times second. So we end up with a, what kind of unit you should end up with? Second, minus 1, or per second, cycles per second. How many cycles? It's 1.46. How many figures should have? How many is it?
2.
2, yeah, that's good, right? That, I think I give you too many. Maybe I see.
Kinetic energy is 2.
So this is 1, should be only 2 seconds. Okay, because I'm just looking at, you have 1 place, 2 places, and then you should only have 1 place, right? Is that good, everyone? What about C? If you want to find out the wavelength, the corresponding wavelength, you will just do that.
Solid
Yeah,
for
just solve for C. Okay, because C times solve for lambda, C the lambda times mu, you know mu, so you see lambda is going to be equal to C over mu, and equal to 3.10, because it's less than 363 times 10 meters per second divided by 1.6 times 10 to the minus 15 second minus 1. So all these cancel out, we end up with what kind of unit?
Meter.
So it should be length unit, right? Because talking about wavelength, so you can have length unit. In this case, it's meter. So I have 2.47 times 10 to the minus 7 and 2 like that. Is that good, everyone? it to you?
And you could like this has 204 millimeters.
Yeah, you could say that is what, 2.0 times 10 to the second, right? Nanometer, just a little bit better, not so many of the exponent numbers. Is that clear, everyone? Okay, let's move on back to the outline. We just finished talking about photoelectric effect. So I just want to re-emphasize this. So light acts or sometimes light appear to behave like a wave. How do I know it behaves like a wave? You can actually measure its wavelength, right, its frequency, and you process what? It could diffract and it could interfere. So those, you can see it in electromagnetic radiation, but at the same time, it behaves like a particle as proven by the photoelectric effect. Okay. So therefore, which behavior you observe depends on what? The experiment. Okay, what you measure. Does it make sense? It's kind of hard to accept. Particle and wave to me is kind of contradict to each other, but it's not. The one you're talking about, not the particle in the sense of little mass, but it's in the sense of particle energy. Okay? Does it make sense, everyone? So let's move to this thing. The next thing we need to know more. We say that we study light to find out something about atoms, like specifically electron in an atom. That's the whole chapter is about, electron in an atom. We find that out through the interaction between light and matter. Okay. The interaction of light and atom give us the information about the electron, about matter. And so how do I find out something about the electron? Okay, so far, not much yet, right? The property of the electron, not too much yet. So what happened, we do a series of something called the spectral, gonna do some experiment using light. So what happened is, by studying the spectrum of the light emitted by energized matter. So say I want to find out something about neons, the electron. Okay, so I will have a tube, and in the tube, inside here, I put in neon gas. So a whole bunch of neon gas, and then energize that by applying electric energy, applying to all the neon inside. All the neon inside, neon atom inside. So the neon now, you inject some energy to it, but once it get that energy, it will re-emit that energy as light. So you just want to say when electricity is passed through a tube, consists of neon, you will gain that energy. But once you gain the energy, you will re-emit that as what? As light. So you can see the light and the electron how you connected now. Okay. So in this case, the light given off is orange red. So neon has orange red light. Okay. So give energy to neon and then let it cool down from excited state back to the ground state. In the process, it give off light could be, in this case, we use the wave function, wave property to represent that. So inject that with more energy, gonna release that light. Okay. So now this light is orange and red looking. Now if I use something else inside, for example, if I use mercury inside, these two mercury particles, mercury gas particles. Again, I energize that. Itchy. So now it's not the orange red light, but rather it's a different kind of light. So in that case, it appears to be blue. Yet another one, if I put helium, say this one is helium inside, and I energize that, and then when you drop that down to its ground state, go to the original energy level, then you would emit lights of a violet light in the middle. And you put hydrogen gas inside here, then you energize that again, and it will give you reddish light. So how come different substance give you different light when you energize?
Do they have different energy?
Yeah, because I will have to analyze these lights. This light